So my name is Julian, I'm a tech evangelist, and I focus on machine learning. In this session, we're going to dive deeper into our machine learning stack, and we'll focus on Amazon SageMaker and a couple of new services around SageMaker that help customers make the most of their machine learning workloads. And we're going to cover all kinds of different things. So you've heard this one before. Our mission, my mission, is to make sure all of you can do machine learning on AWS. And even if you're not a machine learning expert, we think we can help you get started. So that's what SageMaker does. What this session is about is going to the next level, which is now that we all do and enjoy machine learning, can we make it as fast, as efficient, and as inexpensive and cost-effective as possible? So we'll go over different building blocks in the machine learning stack. Let's start with infrastructure and frameworks, the low-level layer that you saw in Boa's presentation. So at reInvent in December, we introduced a new type of GPU instance. It's called the P3DN, so it's still based on the NVIDIA V100 GPU, which is still the fastest GPU available. But we just took the P3 family and we made it more powerful. So what we did is add more of everything. So on the CPU side, we added more cores, more virtual CPUs, because as you scale your large training jobs, it's not just about having GPU power. You also need to have CPU power to run your TensorFlow app or your PyTorch app. And these can be big models, and they need to pump tons of data to the GPU, so they need to run fast. Okay? It's not just about the GPUs. The CPU can become a bottleneck. So we added a bunch of virtual CPUs to those instances. We also added more GPU RAM, because again, as your jobs get bigger, you need more GPU RAM to train faster. So we just double the amount of memory available to GPUs. And more importantly, I think, we made networking even faster. Because when you train on large jobs, first of all, you need to load your data set to the training instances. So obviously, the faster you bring the data to the instances, the better, right? And the second thing is, as you do distributed training, the different instances involved in the training job need to exchange tons of data, right? They need to, at each epoch, each round of training, they need to exchange tons of information. So again, the faster you can do that, the better, okay? So P3DNs for the large distributed training jobs out there. We also improved the C5 family. So the C5 family is the compute-optimized family with the latest Intel architecture called Skylake, which has specific instructions that speed up machine learning jobs. And what we did here is we brought 100 gigabit networking as well, for the same reasons, because some customers train large jobs on C5. They find that pretty effective. But even for prediction, if you have fast networking, the faster the network runs, the more throughput you can get from your instance. So both from a training and a prediction perspective, more networking speed is better. Okay? And just so you know, this is the fastest single core clock speed you can get on EC2 instances. You can get to up to 3.55 gigahertz single core speed. So if you need the fastest, lowest latency single core prediction, this is the instance family to use. But it's not just about hardware. It's not just about instances. We're also working very hard on making the libraries as efficient as possible. So let's talk about TensorFlow for a second. So what this benchmark shows from a few months ago is that we took the vanilla TensorFlow version, and we ran an image classification training benchmark on the C5 instance, okay? And then we optimized TensorFlow using performance patches and collaborating with Intel. And we trained the exact same job on the exact same instance type. And we made it 11 times faster, Okay? So when you use our TensorFlow version running on AWS, and the same applies to other libraries, you just don't use the vanilla version that's available out there. Okay? You get the same API optimized. Okay? So 11 times faster is very significant, because it literally means if you have a training job that lasts for 12 hours, now it's going to last a little more than 1 hour. So during the same day, for the same budget, you can train 11 times more. And machine learning is a very iterative process, so the more you train, the more chances you have to get to the best model. So this is available on SageMaker and on the Deep Learning AMI. You have nothing to do, just import TensorFlow, enjoy speed. We also worked on scaling TensorFlow for large numbers of GPUs. So we noticed that for some customers, training at very high scale, they didn't get the linear speedup that they expected. So specifically when training with 256 GPUs, they would only get 65% of the ideal linear speedup. Okay? And that's pretty bad, because it means the extra GPUs that you add to the problem are not efficient. So you don't spend your money well. Again, we worked on this problem, optimized TensorFlow, and now we have 90% of the ideal linear speedup. So that means pretty much if you double the number of GPUs on your TensorFlow training job, you get almost twice the speedup, all the way to 256 GPUs. Okay, so linear scaling. Again, this is available in SageMaker and the Deep Learning AMI. So to give you an idea of what this means, if we train the ResNet 50 image classifier on a large image dataset with the vanilla version and 256 GPUs, this takes 30 minutes. With the new version, it takes 14 minutes. Okay? So imagine when you're working with 256 GPUs, I guess you have a pretty large dataset, right? So using this optimized version on GPUs, you can slash your training time in half. So 2 weeks becomes 1 week. That's a very, very significant saving, especially with 256 GPUs. We also did some work on Apache MXNet, another open source library for deep learning. So the problem what we're solving here is when you do distributed training, you need to keep the same number of instances and GPUs, if you're training on GPUs, from beginning to end. Okay? So what if, for a very long training job, you actually have extra instances lying around doing nothing? Wouldn't it be nice if you could take those extra instances and add them to the training job and maybe take them back when you need them again? Well, this is exactly what we've done on MXNet. It's called dynamic training, and we can add and remove instances during one training job. Okay? And we do this without losing any accuracy. So if you have reserved instances, for example, lying around doing nothing, why don't you add them to your long-lasting training job and speed things up, right? We're working on implementing this in other libraries, but for now this is only available in MXNet. So I guess that's pretty good for infrastructure and libraries. Now, we can train very fast, we can predict very fast with the C5. Now, what about working on models? Can we make models more efficient? And I'm going to talk about 3 things. I'm going to talk about automatic model tuning, so figuring out automatically optimal hyperparameters for models. I'm going to talk about model compilation, optimizing for the underlying hardware, which is not something where people talk about a lot about when it comes to machine learning, but hey, we think it matters. And model compression, so shrinking models automatically, and this is my Tel Aviv topic. This is the only place in the world I can cover this. So there you go, right? That's the hardcore part of the hardcore talk. Hopefully you'll like it. So let's talk about hyperparameters. So hyperparameters are parameters for the algo itself, okay? So let's say we're working with decision trees. When we set up the training job, we have to decide what the maximum depth for the trees should be and what the maximum number of leaves should be, plus some very esoteric parameters like gamma, ETA, lambda, alpha, and a few more. okay? And the list goes on. So you have to know quite a lot about the algo to get this right. And when it comes to neural networks, again, we need to figure out how many layers we should have and how wide each layer should be and what the learning rate should be for that training job. And if we're working with embeddings, then what should be the configuration for that and how many dimensions and blah, blah, blah. And the list goes on, right? And this is why algos and deep learning are interesting, because they can be tweaked to death. But if you're just starting with machine learning, and even if you're experienced, figuring out the right parameters is pretty difficult. So there are a number of techniques to do this. The first one is manual search, okay? AKA, I know what I'm doing, okay? So I have these 12 parameters for my algo, and I know exactly which ones I should use because I just know what I'm doing, right? Or I read a blog about that, or I saw someone on stage who told me to use those values. I saw this YouTube video, etc. So trust me, no one knows what they're really doing, me especially. So that's not a really good technique, right? The second way of figuring out hyperparameters is called grid search. So it sounds more scientific. So the way grid search works is you start by defining hyperparameter ranges. So again, let's say you have 12 parameters, okay? So you have reasonable values for those parameters. You know, some parameters are by design between 0 and 1, so you're going to explore that. And some other parameters may have a wider range, but you can still figure out reasonable ranges to explore, okay? So now you have this 12-dimension space, okay? And you start by picking maybe 100 random combinations for those 12 parameters, and you train, okay? So you train 100 times, and you look at the accuracies that you get. And the theory says some part of that 12-dimension space will yield slightly higher accuracies than the rest, okay? So you restrict the ranges to this hotspot, and you train maybe 100 more times, okay? Hoping that within that hotspot there is another tinier hotspot, and you do that a few more times until you get to the accuracy that you like or until you run out of budget, okay? And it's really similar to exploring space, right? Space is mostly empty with galaxies every now and then, so find a galaxy, zoom in on the galaxy, and the galaxy is mostly empty. It has a few solar systems, so find the solar system and zoom in on that. And within the solar system, you have a few planets. Hopefully one is more interesting than the others, and you zoom in on that one, right? And then you zoom in on the planet, and you end up in Tel Aviv, right? So that's the theory. Unfortunately, you're going to train thousands of models. It's going to take forever, so it's slow, and it's expensive. So some people said, hey, we need to find a faster way to get to that, to the hyperparameters. So let's try random search, okay? I call that technique spray and pray. And it feels not as efficient as the previous one, right? The previous one felt scientific. Slow, but scientific. This one, not so much. Actually, there's a research paper from 2012 written by the top researchers in AI that show that, on average, this works better than grid search. So just pick 100 or 200 values for the hyperparameters at random, train, just pick the best. Okay? On average, you will get okay models. So fine, faster, cheaper, but it's random. Okay? So how do you explain to your boss or your customer that, yes, you selected this model because it's random? Good luck. So the proper way to do this is to use machine learning, okay? And this is called hyperparameter optimization, and it's what SageMaker does. So you train first few models, maybe 2, 3, 4 models, okay, with random values. And then, using those data points that map parameters to accuracies, you apply machine learning optimization. And if you can't sleep tonight, I highly recommend Gaussian process regression and Bayesian optimization. And those algos predict the next 3 sets of parameters to try. So you train those 3 additional jobs, now you have 6, and using those 6 points, maybe you predict the 3 next ones. Okay, so you don't decide at random what the next 3 jobs should be. They are predicted. They come out of those 2 algos. Okay, so that sounds insane. Let's look at a demo. So here I'm going to use SageMaker, and I'm going to use one of the built-in algos in SageMaker, and this one is XGBoost, right? So popular open source algo for classification. So this gray cell here is what we would do on SageMaker. Use the estimator object in SageMaker, use the container storing the XGBoost implementation, train on one C5 2XL instance, output the model to that location, set some hyperparameters because we know what we're doing, right? So here we're trying to do binary classification on the data set. And we think the trees should be no deeper than 4 levels because we know what we're doing. And we want to train for 1,000 rounds with early stopping at 100 rounds because we know what we're doing, okay? So good luck with that. You can train 100 of those manually, or you can do grid search, and you can explore space forever, and you will never get to the right place. So what we do instead is this, okay? We define hyperparameter ranges. So here I'm optimizing for 4 hyperparameters. So the maximum depth of the trees, actually, because we have multiple trees. And those 3 esoteric parameters, ETA, mean child weight, and alpha, okay, starting from reasonable ranges. So we can have integer ranges, we can have continuous ranges, so floats, and we can have categorical ranges if you want to pass function names, optimizer names, etc., etc. Okay, so I'm defining my ranges. I'm defining the metric I want to optimize on. So here, I want to minimize validation error on this training. Okay. And then, still setting up my estimator in the same way, so using the same XGBoost container, training on one M4 2XL instance. Just setting the mandatory parameter, which is objective. What are you trying to do here? XGBoost can be used in different capabilities. So here I want to build a binary classifier. That's the only one that I set. And then I create my hyperparameter tuning object with the estimator, the metric I'm optimizing on, the ranges to explore, the number of jobs I want to train, and how many I want to train in one go. Okay, so I will train 3 by 3 until I've trained 20. And each time I've trained 3, I will run hyperparameter optimization and predict the next ones. Okay? And then I just get the training going, calling the fit API, just as I would, right? So this trains for a bit, okay? And if I switch to the SageMaker console, okay, I'll see my tuning job here. So I did train those 20 jobs. I can see the metric for each individual job, and if I click on the individual training jobs, I will see the parameters that have been selected and predicted. Or I could just say, hey, just give me the one, give me the best one, right? I'm only interested in the best one. So the best one actually used max depth of 5 and alpha of 1.8997875, which of course is a value you would have figured out manually, et cetera, et cetera. Okay, so now you can just grab this best model from SageMaker and deploy it. Okay, and we also have a notebook where you can visualize the progress of a training job, so we can see all the individual training jobs and their accuracies, and we can plot. Let's just look at this one. We can plot the jobs. So here, that's for the max depth parameter, okay? And then we see the validation error, so obviously lower is better, okay? So we can see the top job is actually that one, okay? And we can see there's a bit of a trend, right? So if we have deeper trees, we tend to increase validation error, because probably we are overfitting the data set, okay? So that kind of makes sense. So it's also a good way to understand what the impact of specific parameters is on your training job, okay? And the only thing that we've done here is to train just 20 times, right? Which is very typical of what you would do. Train, tens of times, not hundreds of times. Now let's move on to the next problem. Okay, so now we have a model that's optimized with respect to hyperparameters. Now, how do we optimize it with respect to the underlying hardware? And again, it's not a problem we usually work on. Okay? Maybe you're surprised that, oh yeah, seriously, we could optimize for the hardware. Unfortunately, it's very complex. Okay, so it's possible you can do it, but it's really manual work, expert work, and every time you train a new model or every time you want to optimize for a new hardware platform, you have to do it all over again. So it's very time-consuming, very time-intensive, and the consequence is most people don't do it. So to solve this problem, we introduced a new service called Neo. And Neo is really two things. Neo is a model compiler. So it will take an existing model in S3. You just write a very simple config file. I'll show you in a minute. And you compile it with a simple API. And by the way, it's free. I know that's important. So you don't get charged for that service. And what you get is an optimized version of the model for the underlying hardware that you can then load on your platform using the Neo runtime, which is a really tiny runtime, much, much smaller than typical libraries like TensorFlow. So in the IoT world, you also save space by not installing those libraries. And you can just load the model with the Neo runtime and predict. Okay? So we've actually open sourced this. So if you have a platform that's close to one of our supported platforms, but not exactly the same one, you can probably port Neo. And if you work for a hardware manufacturer, you're more than welcome to port Neo to your own architecture. So here's an example for the Raspberry Pi. I'm a big Raspberry Pi fan. So here I've got it's a ResNet 50 model, so image classifier that I trained, or you could take an existing model from a model zoo, okay? Just put it in S3, okay? Just declare what that model lives. Declare what the input shape is. So that looks weird, but if you train the model, you would know. Okay, so here, this model is an image classifier. So it takes as input one image with 3 channels, red, green, and blue, color images. And the images are 224 by 224 pixels. Okay, once again, you would know if you had trained that model what the input shape is. It's an MXNet model, and I want to compile it for the Raspberry Pi. And I want the model to be stored in S3 again. Okay? So then all I have to do is run this simple API. So I'm using the command line here. You could use any SDK. And it takes a few seconds for this model. And then I grab the compiled model from S3. Okay? And so I find inside the archive, there's the original model and the compiled version, okay, which is the .so file. So it's a shared object. It's native code for the Raspberry Pi with hardware-optimized version of the math operators used by the model, right? Algebra, convolution, etc. So then all I need to do is copy that to my Raspberry Pi, okay, bottom box, and use the deep learning runtime to load the model and predict. Okay? And when I did this demo on my Pi, I went from 7 seconds per image to about 1 second per image. Okay? So 7x faster. So I'm not promising 7x speed up across the spectrum. Okay? We tend to say on average you'll get twice as fast, but I see better results from time to time. Okay? Once again, one API call, you get this done in 5 minutes, including reading the documentation, and you speed up your model by 2x, 3x, and it's free. So if I were you, I'd give it a try. Okay? So let's see how we can do this with TensorFlow. Why not? Okay, so here I'm training again with SageMaker. I'm training a simple image classifier on the MNIST dataset. Okay, so you've all seen MNIST. digits from 0 to 9, and of course we need to learn how to classify in 10 categories. Okay, so this is a vanilla TensorFlow code. Okay, and I'm training that model on SageMaker. I'm actually doing distributed training here, which is a bit wasteful because it is a tiny data set, but just to show you it's super easy to do distributed training. Just say you want to train on 2 instances. That's all you have to do. Okay, so it trains for a while, a short while. Okay, then I can deploy it the usual way, just called deploy. Okay, so here I'm deploying the unoptimized version, the vanilla version. Okay, and I can invoke it, predict some digits, but what I really want to do is compile it. Okay, so I call that compile model API, passing the target hardware. Here I can optimize. I want to optimize for the C5 family, so the Skylake, the Intel Skylake CPUs. The input shape in this case is 1 sample, 784 bytes, because those images are 28 by 28 pixel, and I flatten them into an array. So 28 by 28 is 784. Okay, and this is a TensorFlow model. Okay, so this compiles just for a few seconds, and then I can deploy it in exactly the same way as before. So .deploy, and voila, as we say. Okay, so obviously for a tiny model like that, the speed up is not what we're, I'm not benchmarking or anything, but with bigger models, you get significant speed up by just doing this. Okay, so it's not even breaking the deployment API. All you have to do is compile a model and then deploy it. Okay, so I don't see any reason why you would skip that step, honestly. It's so easy to do. So now let's get crazy. Okay, so now we have a model optimized for the hardware, and we're happy. But maybe it's a little too big. Maybe I want to deploy on a really small device, or maybe I would like the model to still be faster. So could I have the same accuracy with a smaller model? So less layers, or fewer layers, I should say, fewer layers, and maybe narrower layers. Okay, so intuitively it sounds weird. It's like, well, no. We trained that model, it got to that accuracy, now you want to remove layers and shrink layers, and of course we're going to lose accuracy. So you could try and do that manually and spend your life figuring it out. Or you can go crazy and use a technique called reinforcement learning. So I'm not going to go deep into reinforcement learning. Reinforcement learning is basically a way to solve hard problems, not by building a data set and training an algo, but just by letting an agent experiment in an environment, taking actions, okay, and rewarding positive actions and punishing negative actions. So here, my agent is going to start from a trained deep learning model, and initially it's a stupid agent, so it's going to do silly things. It's going to remove layers that will degrade accuracy a lot, etc. But it's going to do that for a while. And by looking at the actions that the agent took and the results, okay, so did you improve accuracy, yes or no? We're going to give positive or negative rewards. And using a reinforcement learning algo, we can learn from the sequence of actions and the reward. And we can train that algo. And now our agent is a little more intelligent the next time around. Okay, so it explores again. We train again, and the agent becomes a little smarter. And we do that a number of times, okay? And we get to something that works pretty well. So in reinforcement learning terms, we have an objective, which is find the smallest possible model that maintains the original accuracy. Okay, that's the goal, and that's the goal that tells us how to reward actions. If you took actions that yield a smaller model that is as accurate, you get a positive reward. Anything else gets a negative reward. The environment is basically just managing the updated network and training it a bit for a few epochs to see what the accuracy is for the modified network. The state is just which layers did we keep, how big are they, etc. and the actions are, remove layers or shrink layers. And the reward, like I said, is a combination of compression and accuracy. Okay? And if it sounds insane, it is. So we have a sample notebook in SageMaker, which I'm not going to run because I ran it yesterday. I ran it for 6 hours on 5 GPU instances, because it is a bit of a heavy problem. This is actually backed by a research paper. So again, if you want to go crazy, this is the notebook to look for in the SageMaker examples. And so what this one does is it loads a pre-trained ResNet network, and then it lets an agent experiment with removing layers and training it a little bit and measuring accuracy. Okay, and then we can still probably see this training job in the console. Yes. Let's see, 6 hours. Yes, that's the one. And maybe we can look at some of the metrics. Okay, so we see the metrics, but the one I'm more interested in is this one, episode reward mean. So we can see the average reward that the agent gets improves over time. So initially it's very low, and then as it learns to mess with the existing network in a positive way, it gets higher rewards. Okay? And you can see I could keep that thing going for a while, but I felt 6 hours on 5 GPU instances. That was nice enough. Okay? And so all the code is in the notebook. Okay? You can read all about it. And so what kind of result do I get? So after 30 GPU hours, so the original model had an accuracy of 0.81, okay, 81%. And so after those 30 GPU hours, I get to a model that's the lowest one here, 3.66 times smaller, okay, so almost 4 times smaller, with a base accuracy of 0.7, okay, knowing that this accuracy is only measured after a few epochs. So if I took that model and trained it properly for as long as I've trained the original model, I would get very close to 0.81. Okay, so pretty much same accuracy, about 3 to 4 times smaller. Okay, and if you train a little longer, you can get to even smaller networks. Okay. All right, so now if you have a headache, it's my fault. But hey, I have a headache too. Yeah, flu at 3 a.m., I recommend it. Okay, so one last thing. So we've seen how to optimize hyperparameters, right? We've seen how to optimize for the underlying hardware, so speeding prediction up. And we've seen how we could even shrink using that crazy reinforcement learning technique, how we could shrink the model without losing accuracy. But coming back to more reasonable things, we should look at optimizing prediction, because we get all excited about training, right? A lot of people focus on training times, optimizing training, and why not? But what our customers tell us is that 90% of their spend is actually on prediction. And that makes sense, because you train once in a while and then you deploy, and if you deploy at scale, you maybe have 10, 20, 50, 100 instances running 24/7 doing prediction. So those costs will add up, okay? So the legitimate question is, since this is the bigger chunk of your machine learning spend, are you making the most out of that? And we see some problems here. When you deploy to CPU or GPU instances, sometimes the models are not complex enough to keep the instance busy, right? The NVIDIA V100 chip that I mentioned, it has over 5,000 GPU cores. Okay, so you need to have big models to keep those cores busy. Less complex models will only use a fraction of that, okay? And the same goes for virtual CPUs on CPU instances. So it's not obvious that you make the most of the hardware. And then every model is going to be a little different, right? So some models will run nicely on a CPU instance. Some will require a GPU instance. Some will require a GPU instance while not making full use of it. So, that CPU versus GPU split is a little restrictive. So that's why we invented this new service called Elastic Inference, and it's very easy to understand. So Elastic Inference lets you attach acceleration to any CPU instance. Okay, so this works on Amazon EC2, Amazon SageMaker, notebook instances, and prediction endpoints. So you actually deploy to a CPU instance, but you attach fractional acceleration between 1 to 32 teraflops. Okay, so you have 3 sizes: medium, large, X large. So you can experiment with that. So now you get to a performance level that's close to what you would get with a full-fledged GPU instance. Okay, but you get a huge discount. So if you combine a C5, I think a C5 medium with the, I think the XL accelerator, or the large accelerator, and you compare that to a P2 XL instance, you get pretty much to the same level of performance as P2 XL, which is the cheapest GPU instance. Okay, you get within, let's say, 10%, but it's 75% cheaper. Okay, so if you deploy to GPU instances today, I would highly recommend that you try this. Okay, try the different sizes of acceleration, deploy to C5 instead, plus an accelerator. Try the 3 sizes, make sure the performance is okay with your app, and then compare the costs. Okay, and then yell at me on Twitter if you didn't save a ton of money. Right? I'm used to it. Okay, let's take a look. So here we're going to look at an MXNet example. And I'm not going to train a model here. I'm going to grab a model in ONNX format. So as you may know, ONNX is an interoperability format for MXNet and PyTorch and a few other libraries. So libraries can exchange models. So here I will just download the ResNet 152 image classifier in ONNX format from the web. I will just upload it to S3, okay? And then I create it, okay? I register it, so to speak, in SageMaker. And this is an MXNet model, okay? So now I can deploy it. And, well, this is pretty disappointing, which is the way I like it, because it means it's simple. All you have to do is this, okay? Model.deploy, instance count, instance type, accelerator type, okay? So comparing to GPU deployment, you just need to change the instance type to CPU and specify an accelerator type, okay? That's it. So if you want to use if you don't want to use SageMaker, if you want to use the deep learning EMI, you'll find in the deep learning EMI MXNet and TensorFlow APIs to use acceleration. Okay, there's a tf.contrib API that extends the TensorFlow estimator to work with the elastic accelerator, and we have a similar feature in MXNet. So you can either use this managed in SageMaker or build it yourself using the APIs that we added. Okay? So that's pretty simple. So we're trying to make machine learning accessible to everybody. And with those new services, we think we make those workloads faster for training, faster for inference. So you save time, training time, prediction time, and time is money. So you will save a lot of money, especially with that elastic inference, and no plumbing, right? Hyperparameter optimization, super simple to use. Neo, one API call, and it's free. Elastic inference, one extra parameter in your deployment API calls on SageMaker. Okay, so no reason not to use those if you ask me, but that's just me. So you should go and try and tell us what you think. So if you want to get started, I would recommend going to the SageMaker page where you'll find information on the services and customer stories, pricing, documentation, etc. I highly recommend the collection of notebook examples on GitHub. Some of my demos came from that today. There are plenty more, and this is really the best way to understand how SageMaker works. They're available on GitHub, and they're also automatically available on notebook instances when you create them. And you can take a look at my blog where I have quite a bit of SageMaker and deep learning content. So you might find that useful too. So thank you very much. I hope this was useful. You can stay in touch on Twitter. Send me feedback. Tell me what you've tried. I'm happy to get your opinion on those services. If you build cool stuff, let me know. And again, I'm more than happy to retweet and share with the community. So thank you very much. I'll come back later this afternoon to talk about inference pipelines and Spark. So if you want an even bigger headache, please stick around. Thank you very much.